Hello, and welcome to section 5.5, the substitution rule. In this section, we're going to see how to turn more complicated integrals that we don't know how to find the antiderivative of into simpler integrals where we do know how to find the antiderivative. And we've used the method of substitution in other forms in the past in algebra. So if you think back to an equation like this. So we don't know how to solve that as is, but we can recognize that as a quadratic form. So here you have e to the x is squared, here you have 3e to the x, and here you have a constant. So we could make a substitution. You could say let u equal e to the x. Then you can rewrite this in terms of u. It's a quadratic in terms of u. And you can solve it because you know how to solve a quadratic equation. Then you make your substitutions back, so you replace u with e to the x in your solutions, and then you solve for x. So that's the type of thing we're going to be doing here. But it's a little more complicated because integration is a little more complicated than solving an equation from algebra. We're also going to refer back to the differential. So let's look at an example. Here's a simple example, the indefinite integral of the cosine of pi over 2t. So this is not simply equal to the sine of pi over 2t because you have a composite function, right? And when you take the derivative of sine of pi over 2t, it should equal this. But I know that using the chain rule, the sine of pi over 2t is going to be pi over 2 times the cosine of pi over 2t. Remember, the derivative of the inside times the derivative of the outside. So I need to do more work, but that is a good place to start. Let's make like we did with our algebraic example where we found a piece of the equation and we simplified it by setting u equal to that. Let's do the same thing here. With our composite function, let's set u equal to this inside function, pi over 2t. So if u is equal to pi over 2t, then my integrand turns into just cosine u, and I know how to find the antiderivative of that. But that means I'm turning that whole integral into something in terms of u. So we can't forget the du, right? That's the differential that's always tacked on to the end of the integral. So let's take a step back and look at what we're doing. So if we're saying that I'm going to make a substitution, and because the antiderivative of cosine u is sine u, what happens when I find the derivative of sine u with respect to u? Well, it's the derivative of the outside function, which would be cosine, evaluated at the inside function, which is pi over 2t, times the derivative of the inside function, which is pi over 2. So I see that just saying replacing pi over 2t with u is giving me an extra factor of pi over 2 when I find the derivative of sine u. So I need to do a little bit more work. So this is where the differential comes in again. So that dt that we've seen tacked on here is actually a differential. And if we think of our substitute variable here, our substitute function u, du, the differential of u, is just the derivative of u of t, which is pi over 2 dt. So remember, I need to get my entire integral in terms of u, not t, so that I can find the antiderivative and simplify things. So if we let u equal pi over 2t, then du is pi over 2 dt. That's that differential. So now I can simply solve for dt to get it in terms of du, and now I can make the substitution for every part of my integral. I have the cosine of pi over 2t times dt equals, if I substitute u everywhere I see pi over 2t, I get cosine u. If I substitute 2 over pi du everywhere I see dt, I end up with this simplified integral. And this I know how to find the antiderivative of. So this is simply 2 over pi sine of u plus c. And then if I put it back in terms of the original variable t, it's 2 over pi sine of pi over 2t. So what we did here was made sure we replaced every part of the original integral to make it in terms of the new variable. So we can't just look at the function, we also need to look at that differential and get the new differential in terms of the old, or the old differential in terms of the new, depending on how you look at it.